on to introduce the final speaker for today. I'm delighted to be joined by Javier Alvarez-Valle from Microsoft Research. Javier, I understand, is leading the InnerEye project at Microsoft Research, and he's going to talk about democratizing medical imaging AI. Javier, if you're able to share your screen, we'll see how this works.
Okay.
That looks good. Yeah, go ahead.
Is it working?
Yeah, it's working perfectly. Yeah.
Okay. Yeah, thank you for the introduction. Yeah, good afternoon, everyone. I'm Javier. Yeah, I'm leading medical imaging AI at Microsoft Research in Cambridge. So I'm part of the InnerEye project. And in the InnerEye project, basically our mission is to empower healthcare organizations to build a state-of-the-art AI models in the cloud using Microsoft Azure to ultimately benefit patient outcomes. And today I'm going to talk to you about two topics. The first one is going to be about our radiotherapy work. And the second one is going to be about how we are realizing this mission by using open source software. Okay, so when we talk about cancer treatment, there are three main ways that we use for cancer treatment today. The first one is surgery, where we remove the tumor from the patient body. The second one is chemotherapy, where we use drugs to kill cancer cells. And the third one is radiotherapy. Radiotherapy is a key component of cancer treatment, and is being used in 40% of the patients that are being cured from cancer today. Sorry. In order to plan the radiotherapy treatment, we use a linear accelerator to basically program the linear accelerator. We have to take a CT scan, and then a clinician has to delineate the CT scan manually, and this usually takes between 30 minutes to 2 hours. And this has to be done in 3D. So basically, yeah, it usually takes a long time, and it depends on the cancer type. So when we look at the standard clinical workflow of radiotherapy, first we need to take a CT scan. Then we have to do the manual delineation, and then we have to do the dose calculation. And the patient has to come into the clinic for multiple fractions to deliver the treatment. And as you can imagine, during these fractions, the body of the patient might change. And currently we only plan radiotherapy once because this manual delineation process is very expensive. So what we are proposing with InnerEye is to augment the clinicians by helping them with AI models that will accelerate the radiotherapy planning. So when we put InnerEye in this workflow, we not only reduce the time to deliver the treatment, but we also enable new workflows. So for example, we can start replanning after a few fractions, and we can enable what we call adaptive radiotherapy. So in order to evaluate this technology that we developed over the years, last November, we published a paper with our friends at Addenbrooke's Hospital titled Evaluation of Deep Learning to Augment Image-Guided Radiotherapy for Head and Neck and Prostate Cancers. And in this paper, we try to answer the question of can machine learning models achieve clinically acceptable accuracy in image segmentation tasks to reduce planning and reduce the overall contouring time. In this study, we follow a couple of guidelines. So we follow this guideline that basically talks about what are the key challenges to delivering clinical impact with artificial intelligence. And we also follow the Consort AI guidelines for clinical trial reports with interventions involving artificial intelligence. And basically the contributions from our study are the following. First, we reduce the time of segmentation in radiotherapy by a factor of 13 times. We integrated these models seamlessly with the clinical workflow, and we show how these models can generalize across internal and external data sets. And we did this both for cases of prostate cancer and head and neck cancer. So we show how this can generalize across different body parts. So the way we integrated these models into the clinical workflow was using the InnerEye gateway, this InnerEye inference component, and this InnerEye training. These three components are open source and you can access them in GitHub. With the InnerEye training, you can train models and register them in Azure Machine Learning Services. Once they are registered, you can run inference using the API. And then the InnerEye gateway actually connects the hospital with the cloud. So when you get a CT scan from the scanner, it goes into the patch, and then we can actually call the gateway automatically once a new image is inserted. And the gateway will basically decide what machine learning model needs to be executed based on the DICOM tags on the image. Then the gateway will anonymize the image, send it to the cloud, and wait for the segmentation to be performed on a GPU cluster. And then once we get back the segmentation, the gateway will de-anonymize the image and put it back into the database. And basically, once the clinician goes to see the CT scan for planning radiotherapy, they already have the segmentation ready and they can start reviewing it or reusing it for dose planning. So one of the problems with machine learning models is generalization. So many studies, they don't look at testing their AI models across different centers. And something that we have done in this study is to actually collect data from different hospitals around the world. So we have data from New Zealand, Australia, Europe, North America, and South America. And we also look at two cancer types, as I said, head and neck and prostate. And the way we structure our data set was the following. For prostate cancer, we took 5 sites for training and validation. We took 2 sites for external validation. And for head and neck, we took 2 sites for training and 1 site for external validation. And as you can see, they are from different regions, different scanner types, and different image resolutions. They also have different patient preparation. So patients are not being prepared for radiotherapy treatment the same way in all the centers. The technology that we used to perform segmentation was a unit 3D, but we actually did several improvements to the standard unit 3D, and we optimized the network to perform really well based on the hardware available in the cloud. So we actually use mixed precision training and all kinds of optimization tricks to be able to fit the biggest patches possible at training time to get really good contextual information and get the best results. Then we ensemble 5 models into a single model. And we can do this using Microsoft Azure Machine Learning Services, leveraging 20 B100 GPUs. To perform inference, we actually did several optimizations as well. So we wanted to be able to fit the entire city volume into the GPU to perform inference. And this allows us to basically eliminate the need to create patches. So this gives us better contextual information, better batch statistics, and we can train really large models with 32 million parameters. And this gives us the best results. So we partition the model across 4 GPUs in a node with 4 GPUs, and then we can process in one go the entire volume. The metrics that we used to evaluate the models was dice score and Hausdorff distance. As you probably know, dice score is just intersection of a union, and Hausdorff distance is the longest distance between the ground truth contour and the predicted contour. And this is actually quite helpful to identify where the model is making the worst mistakes. Here there is some evaluation, qualitative evaluation of the results for the main data sets and the external data sets. And as you can see, there is no apparent difference between the predicted contours in the training set and external data sets. Here we have the same for head and neck. And actually in this external data set, you can see that we have beam hardening artifacts and metal artifacts, and the model still performs really well. We actually did a statistical testing for all these structures. So this is a comparison of, so in blue we have the external data set, and in orange we have the internal data set. And here we are comparing the prostate structures. And we can see that all the structures are above 80%. The dice score of 80% is already really good for clinicians, and they consider this within the inter-observer variability. And for example, here seminal vesicles are a small structure, so you will always get lower dice scores because small error will influence the dice score more than in bigger structures. But yeah, with statistical testing, we have seen no difference between internal and external data sets. In terms of measuring the clinical value of these models, we perform an experiment where we basically took 10 CT scans for head and neck, and we asked clinicians to annotate them manually, and also to take the output of our model and correct that output. So we have seen a reduction on time from 73 minutes to 5 minutes. This is more than 30 times time savings. And this is only for 10 structures. The models that we have deployed with Addenbrooks for research evaluation have 22 structures. So these time savings should be even bigger in reality. The other thing that we have done is inter-observer variability analysis. So we had 3 radiation oncologists annotating the same image for different structures. And here we have rectum. So then we basically aggregated the contours from the 3 of them using the majority voting. And we performed a statistical agreement analysis using kappa stats and Bland-Altman plots. And here is some qualitative results from the analysis of the inter-observer variability. So this is a prostate case. And this is the first, this one is the output of the model. These are the 3 experts, and these green and red colors here basically represent surface distance to the ground truth, which is the majority vote. And what we can see here is that actually the errors are concentrated around the boundaries of structures with other ones. So for example, here, this is the boundary between prostate and rectum. And this is actually, the errors that the model is making is exactly the same as, or very similar to expert number 1. So you can see that the red areas are very similar to what the expert number 1 is doing. Now, we also did a statistical testing for inter-observer variability. So here you can see an analysis on the inter-observer variability cases, comparing the model with the majority voting. And then what we can see here is that the model is performing the same way as the oncologist, and in some cases it's actually even more consistent than the oncologist, comparing with the majority voting. So when we look at the head and neck cases, we also see the similar results. So we didn't observe any statistical difference. And finally, the last thing I wanted to say about the radiotherapy work is that we are now trying to deploy this clinically in Addenbrooke's. So we basically announced last December that because we are open sourcing all our code, Addenbrooke's is going to basically retrain the models using their data in their own Azure subscription. And they are going to go through clinical validation and create a quality management system to put this into clinical use. So we have been evaluating this for 3 years already with them in research evaluation, and they now want to move it to clinical use. Now let me tell you about the open source toolkit that we have. So the goals that we have with open source is to make our research results transparent and reproducible, and build trust with healthcare organizations. And we want to help any organization that want to build state-of-the-art AI models to have a framework where we can build very easy segmentation models. They can follow the best practices for AI models. So we follow all the ML ops criteria and checklist to basically make sure we produce really high quality models. And then we also offer you a framework to leverage the cloud and make the best use of this technology. So why, you might be thinking now, okay, why do I need to move to the cloud? I'm really happy with my local cluster and my GPUs under my desk. So the reasons are basically that you don't want to be buying GPU clusters every few years and maintaining these machines. You can basically rent them from the cloud and use them on demand. So basically, if you have a small team, you pay for what you use, and if you want to grow your team, you can basically start scaling to bigger clusters without having to acquire new hardware. The other reason is that you don't want to pay for what you don't use, and you get access to the latest hardware. So every year there are new GPUs, and you want to be using the latest ones, right, to produce the best models. There are also other features that are available in the cloud, like confidential computing and other things that might not be available in your local cluster. The other benefit of using our open source with these Azure machine learning services is that it allows you to work as a team. So it's all designed to make experimentation transparent, so you can see who is running what experiment. It's all traceable, so you get a record of what code was used to train that model, what model settings were used, and it's all reproducible. So you should be able to go to one of the experiments and reproduce what your colleagues are doing. And every model that is built with our toolkit gets registered into this Azure Machine Learning Services registry. So you can basically deploy it with the inference, deploy any of the experiments that you are running into production. So you don't have to do any extra work. Other features that we have in the toolbox is like basically different levels of abstraction. So if you want to use segmentation models like the ones that we have for radiotherapy, you can work at very high level. So you can basically just modify a small configuration and train the same models that we are building for radiotherapy. If you want to go low level and build different networks that are not available in the toolkit, you can do that. We have a way to plug in with PyTorch Lightning and bring your own models. We provide like reporting and diagnosis. We do model comparison. So you get this statistical testing all for free for segmentation models. So we will take a previous experiment that you ran for your model and compare all the structures and see if your new version of the model is actually better than the previous one. It allows you to write less boilerplate code, so you can reuse most of the things that we have done already for training in the cloud. And yeah, you can leverage this Azure Machine Learning service off the shelf. So now let me show you how you can build a segmentation model using our toolkit. You can basically use our DICOM to Nifty converter. So you can run a very simple tool that will take all your Nifty files and generate masks. So we'll basically convert the contours into masks. I will create this dataset CSV file with all your subjects. You will have here like all the structures and the CT scan. And this will go into the model as the data set. So you will upload your data set CSV and all the Nifty files to your Azure data storage. And then you can define the structures that you want to segment, the channels, and change a few things. And you should be able to start training your model with a simple Python command. So we can use our runner and specify, okay, I want to run the model called lang, and I want to run it in the cloud. So you can pass this Azure ML equals true. If you don't want to run it in the cloud, you can run it on your own machine for development purposes as well. And you just don't pass that parameter. And if you have GPUs on your machine, you can run it there as well. Then once you submit the experiment, you can go to the dashboard, keep track of all the experiments, see what arguments were used to train that model, look at the Git commit that was the last one to submit that job. You can look at the logs that the training of that machine learning model is producing. You can look at the metrics, so you can see, okay, what are the dice score on the training set for these different structures, and you will see plots. The other thing that you can do as well is to see a snapshot of the code that was used to train the model. So you don't even need to go back to Git. You can just from here see exactly the code that was used to train the model. And some additional capabilities that we have in the toolkit are basically cross-validation. Okay. So you can build multiple models in parallel. So if you want to basically split your data into 5 folds, we will basically create 5 different experiments that will run in parallel, and you will see the cross-validation report. But you can also ensemble these 5 models into a single one that you can immediately deploy into your clinical workflow. You can do hyperparameter tuning. As I said, we have this bring your own PyTorch lightning model framework where you just implement an interface and get all the benefits of training in the cloud. And then we recently added this self-supervised training feature where you can actually leverage this bootstrap your own latent model or SimCLR. And let me show you this last feature a bit more in detail because we have been using this for our COVID work. So yeah, with this self-supervised learning, we allow you to leverage and label data sets. So we allow you to pre-train models on data that does not contain any labels and generate really good features and initializations for your downstream models. So this builds on top of this bring your own model framework. So this is a good example if you want to build on top of our work and customize your own model. It supports multi-data sets, so you can basically do self-supervise on one data set and then monitor the pre-training of that model on a different data set. So you can basically do this with, let's say for X-rays, you want to pre-train with Chexpert, NIH, or this RSNA pneumonia challenge. You can pre-train on those data sets and then have your downstream task data set for monitoring when that pre-trained model is achieving good results. And these models bootstrap your own latent and SimCLR. They require a lot of data augmentation. So we actually created a flexible augmentation pipeline. And yeah, so we have been using this feature for a project that we have with University Hospitals Birmingham. So we have been helping them to create a model that extracts features from chest X-rays. So the idea is that we want to create a triage model for COVID-19. So they have been looking at the British Society of Thoracic Imaging guidelines, and in these guidelines, basically, they create a model to triage patients, and this is based on multimodal data. But one of the components of that workflow is checks X-ray. So we have been building a model that extracts features from X-rays, and basically it's a hierarchical model. First, it basically checks if there are suggested COVID-19 features. If there are, then it goes and tries to classify if the features are classic features of COVID, and then we classify that as CBX1. And if there are no classic COVID features, then we classify it as an indeterminate or CBX2. And if there are no COVID features in the X-ray, then we check if there are other pathologies. So we see if there are other conditions, like for example, heart failure, or if there is actually, this is just a normal X-ray. So here, what I'm showing you in this plot is basically the PRAUC for 5 folds. And we have 2 models. One is trained from scratch using 6,000 images from Birmingham. And the other one is pre-trained on NIH data. And then fine-tuned on these 6,000 X-rays from Birmingham. And what we can see is that actually we see improvements of up to like 5%, 9% and 8% on this hierarchical model, trying to classify these 4 classes. So yeah, if you want to try some of these features that we have in our toolkit, I encourage you to take a look. You can access it here through aka.ms InnerEye OSS. And we have lots of documentation. As you can see here, we have been working as well on this Fast MRI challenge. And you can take a look at this as well. So we have some scripts to pre-process the data. And then you can basically use distributed training to accelerate experimentation for image reconstruction. And if you have any issues, just open an issue. And if you want to contribute to our code, please send us a pull request. And yeah, this is the team. And yeah, that's everything that I have for today. If anyone has any questions. Sorry, there was a lot of noise because there was a big storm here in Cambridge.
Thank you so much, Javier. That was a really fantastic talk, overview of an absolute ton of work that you and the team have been doing. I was interested particularly in the COVID work that you've been doing with Birmingham. It seems fairly similar to what we've been doing that Mike was talking about as well. There is a question in the chat. It's from Marina Romanchikova. I don't know if Romina is here or able to speak, but if not, I can read it out for everybody to listen to. Marina says, how do you explain the large systematic difference between AI human observer for parotid glands? And I guess this is in reference to the head and neck cancer comparison.
Yeah, I think the submandible glands, there was a bit of difference. And I think this was because in some cases there was low contrast, or in some cases there are resected submandible glands. So maybe the patient doesn't actually have them. And the model might have tried to segment a bit of that gland there. But this is something that the oncologists can easily fix, so it won't take them any time. And it's like a special case. We had a few examples of resected glands on the data set.
Okay.
Yeah.
Hopefully that answers Marina's question. Anybody else with any questions? Maybe I can ask one quick one myself, just about the use of the Azure cloud computing system for doing some of this work. And you were talking about the advantages over a local clusters. Just in terms of data security and information security when we're dealing obviously with patient data.
Yeah.
What kind of checks and balances have you put in place to make sure that everything is up to standard there for access to anonymized patients' data? Yeah, so we are actually working on a trusted research environment, and we are going to open source this work as well. So in this trusted research environment, what we are going to provide is a way to basically, with one-click deployment script, to be able to deploy all the infrastructure that you need to host an environment where data cannot go out. And we are hoping to make sure that it follows all the HIPAA checks. And
And yeah, basically the cloud sometimes could be even more secure than on-prem. So usually everything is kept up to date. There are security features in the cloud that will actually check that all your configuration is correct, so you can actually verify that you don't have any ports open, and it's all automated. You don't need to have an IT administrator checking this manually.
Great, that's good to hear.
Yeah.
Any more questions, Carola, John? Anything to ask Javier before we wrap up for the day?
No, thanks a lot. Really great talks by both Javier and Mireia. Really very, I think, James, you also said that, very impressive, all the work that has happened here in Cambridge in the different groups. So it's good to bring us all together to discuss more.
Yeah.
Yeah, likewise, just really impressive work from both.
Thank you.
Brilliant. I think, well, if there are no further questions, we will finish just a couple of minutes early. I think the plan, Claire, is to reconvene tomorrow at 10 o'clock in the morning, where we have some talks from some more of the Cambridge postdocs working in the centre. Plus, after a short break, we'll hear from Mihaela van der Schaar and Zoe Kortzi, and the meeting is scheduled to finish just after 1 o'clock, so 3 hours tomorrow, basically. And that will complete the session for today. Anything else to add, Claire? Any housekeeping